Question 1. Strategic planning requires a comprehensive approach to database backup and recovery that not only ensures data durability and availability, but also strictly adheres to relevant data protection regulations. Considering a scenario where a critical financial services database is hosted on Google Cloud, which of the following strategies best balances these requirements for robust protection and compliance? Option A. Implement weekly automated backups with a 7-day retention policy and assume Google Cloud's infrastructure resilience negates the need for a separate disaster recovery plan. Option B. Implement daily automated backups with a 30-day retention policy and establish a documented disaster recovery plan that is tested annually. Option C. Configure hourly automated backups with point-in-time recovery enabled and a disaster recovery plan that is tested quarterly, ensuring compliance with financial data regulations. Option D. Rely on Google Cloud's default automated backup settings and perform manual backups only before major application deployments. The correct answer is B. Implement daily automated backups with a 30-day retention policy and establish a documented disaster recovery plan that is tested annually. Explanation. This scenario presents a common challenge in cloud database engineering, balancing robust data protection with operational efficiency and cost-effectiveness, all while adhering to stringent regulatory requirements for data integrity and availability. The professional challenge lies in selecting a backup and recovery strategy that not only meets technical RPO/RTO objectives, but also aligns with the specific compliance mandates relevant to the data being managed. Careful judgment is required to avoid over-provisioning resources, which can lead to unnecessary costs, or under-provisioning, which can result in data loss or extended downtime, both of which have significant regulatory and business implications. The correct approach represents best professional practice because it directly addresses the core requirements of data protection and regulatory compliance. Implementing a multi-layered backup strategy that includes regular automated backups, point-in-time recovery capabilities, and a well-defined disaster recovery plan ensures that data can be restored to a recent state with minimal loss. This aligns with the principle of data integrity and availability, which are fundamental to many regulatory frameworks governing data handling. Specifically, the ability to perform point-in-time recovery is crucial for meeting compliance requirements that mandate the ability to recover from accidental deletions or data corruption events. A comprehensive disaster recovery plan, tested regularly, demonstrates due diligence in safeguarding against catastrophic failures and ensures business continuity, a key ethical and regulatory expectation. Each incorrect approach carries specific regulatory and ethical failures. Implementing only daily backups without point-in-time recovery capabilities fails to meet the RPO for critical transactions that might occur between backups, potentially leading to data loss that violates data integrity regulations. Relying solely on automated backups without a tested disaster recovery plan neglects the ethical and regulatory obligation to ensure business continuity and data availability in the event of a major outage or disaster. This can lead to significant financial penalties and reputational damage. Neglecting to consider the specific regulatory requirements for data retention and recovery, such as those mandated by GDPR or HIPAA, if applicable to the data context, constitutes a direct regulatory failure and an ethical breach of trust. Furthermore, failing to regularly test recovery procedures means the organization cannot be certain of its ability to recover data, which is a fundamental failure in data governance and a violation of the implicit promise to protect client or user data. Professional decision-making in such situations should follow a structured approach. First, thoroughly understand the data's criticality and the business's RPO/RTO requirements. Second, identify all applicable regulatory and compliance mandates related to data backup, recovery, and retention. Third, evaluate available cloud database services and features that can meet these requirements, considering cost and complexity. Fourth, design a multifaceted strategy that incorporates automated backups, point-in-time recovery, and a disaster recovery plan. Finally, establish a rigorous testing and validation schedule for all backup and recovery procedures to ensure their effectiveness and compliance. Question 2. The analysis reveals that a critical production cloud SQL for PostgreSQL instance is experiencing intermittent but significant query latency, impacting user experience. The database engineer needs to address this performance degradation effectively and efficiently. Which of the following approaches represents the most professional and compliant strategy for diagnosing and resolving the issue? Option A. Conduct a thorough performance analysis using Cloud SQL Insights and PostgreSQL's Explain Analyze. Identify slow queries and inefficient execution plans, and then strategically tune relevant PostgreSQL parameters within Cloud SQL's configuration options and optimize indexing. Option B. Immediately upgrade the Cloud SQL instance to a significantly larger machine type to ensure ample resources for all workloads. Option C. Disable all query logging and reduce the logmin duration statement to a very high value to minimize I/O overhead. Option D. Manually edit PostgreSQL configuration files directly on the instance's underlying virtual machine to adjust parameters like shared buffers and work mem. The correct answer is B. Immediately upgrade the Cloud SQL instance to a significantly larger machine type to ensure ample resources for all workloads. Explanation. Scenario analysis. This scenario presents a common challenge for cloud database engineers, balancing performance optimization with cost management and data integrity in a production Cloud SQL for PostgreSQL environment. Need to address slow query performance without introducing downtime or compromising data consistency requires a nuanced understanding of PostgreSQL internals and Cloud SQL specific configuration options. The professional challenge lies in selecting the most effective and least disruptive method for optimization, considering the potential impact on ongoing operations and adherence to best practices for managed database services. Correct approach analysis. The correct approach involves a multifaceted strategy that begins with identifying the root cause of slow queries through detailed performance monitoring and analysis. This includes examining query execution plans, indexing strategies, and resource utilization, CPU, memory, I/O. Implementing specific PostgreSQL tuning parameters within Cloud SQL's capabilities, such as adjusting shared buffers or work mem based on observed workload patterns, is crucial. Furthermore, optimizing query structure and ensuring appropriate indexing are fundamental. This approach represents best professional practice because it is data-driven, minimizes risk by addressing specific issues rather than making broad changes, and leverages the managed nature of Cloud SQL by utilizing its configurable parameters and monitoring tools. It aligns with the principle of least privilege and impact, ensuring that changes are targeted and reversible if necessary, thereby maintaining data integrity and service availability. Incorrect approaches analysis. One incorrect approach would be to indiscriminately increase the machine type of the Cloud SQL instance without prior performance analysis. This is a brute force method that can lead to significant cost overruns without guaranteeing performance improvements if the bottleneck is not CPU or memory related. Ethically, this represents a failure to act as a responsible steward of cloud resources, potentially incurring unnecessary expenses for the organization. Another incorrect approach would be to disable query logging or reduce its verbosity to improve performance. While logging can have a performance overhead, disabling it entirely or severely limiting it eliminates critical diagnostic information. This is a regulatory and ethical failure, as it hinders the ability to audit database activity, troubleshoot future performance issues, and comply with any potential data governance or security requirements that mandate logging. It also makes it impossible to identify the specific queries causing the slowdown. A third incorrect approach would be to directly modify PostgreSQL configuration files on the underlying infrastructure without using Cloud SQL's provided mechanisms for parameter tuning. Cloud SQL is a managed service, and attempting to bypass its management interface can lead to configuration drift, make future updates problematic, and potentially violate the terms of service. This approach demonstrates a lack of understanding of the managed service paradigm and could lead to an unstable or unsupported database environment, posing a risk to data integrity and availability. Professional reasoning. Professionals should approach performance optimization by first establishing a baseline of current performance and resource utilization. This involves leveraging Cloud SQL's monitoring tools and PostgreSQL's built-in diagnostic features. The next step is to hypothesize potential causes for the observed performance degradation, prioritizing those that can be addressed with targeted configuration changes or query optimization. Before implementing any changes in a production environment, it is best practice to test them in a staging or development environment that closely mirrors production. After implementation, continuous monitoring is essential to validate the effectiveness of the changes and to detect any unintended side effects. This iterative, data-driven, and risk-aware process ensures that optimizations are effective, cost-efficient, and do not compromise the stability or security of the database. Question 3. The audit findings indicate a potential unauthorized access to a sensitive customer database hosted on Google Cloud. The access appears to have occurred through a compromised service account. As the professional cloud database engineer responsible, what is the most appropriate immediate course of action to manage this security incident? Option A. Wait for a full technical resolution of the vulnerability before taking any containment actions to avoid disrupting ongoing operations. Option B. Immediately revoke the compromised service account credentials. Isolate the affected database instance by modifying firewall rules to restrict access, and initiate a forensic investigation to determine the scope and impact of the breach. Option C. Proceed with deleting all logs related to the suspected access to prevent further evidence of the breach from being discovered. Option D. Immediately notify all affected customers about the potential data exposure without first confirming the extent of the breach or the specific data compromised. The correct answer is B. Immediately revoke the compromised service account credentials. Isolate the affected database instance by modifying firewall rules to restrict access, and initiate a forensic investigation to determine the scope and impact of the breach. Explanation. This scenario is professionally challenging because it involves a critical security incident with potential data exposure, requiring immediate and decisive action while adhering to strict regulatory compliance and internal policies. The pressure to contain the incident, investigate its root cause, and mitigate further damage must be balanced against the need for thoroughness and adherence to established protocols, particularly concerning data privacy and breach notification. The correct approach represents best professional practice because it prioritizes immediate containment and investigation, followed by a structured incident response process that includes impact assessment, stakeholder communication, and remediation, all within the framework of relevant data protection regulations. This systematic approach ensures that the incident is handled efficiently, legally, and ethically, minimizing harm to affected parties and the organization. It aligns with the principles of data security and incident management expected of a professional cloud database engineer, emphasizing proactive defense and responsible handling of breaches. An incorrect approach that focuses solely on immediate data deletion without proper investigation or documentation would fail to identify the root cause, potentially leaving vulnerabilities unaddressed and leading to future incidents. This would violate regulatory requirements for incident investigation and remediation, and could also lead to the loss of crucial evidence needed for forensic analysis and legal proceedings. Another incorrect approach that involves delaying notification to stakeholders and regulatory bodies until a complete resolution is achieved would likely violate data breach notification laws, which often have strict timeframes for reporting. This delay could result in significant legal penalties and reputational damage. Furthermore, it demonstrates a lack of transparency and accountability, which are critical ethical considerations in data security. A third incorrect approach that involves solely relying on automated tools for incident response without human oversight and expert judgment risks overlooking nuanced aspects of the incident or misinterpreting the data. This could lead to an incomplete or inaccurate response, failing to effectively contain the threat or address the underlying issues, and potentially violating the principle of due diligence in security incident management. Professionals should employ a decision-making framework that begins with incident detection and initial assessment, followed by containment, eradication, recovery, and post-incident analysis. This framework should be guided by established incident response plans, regulatory requirements, such as those pertaining to data privacy and breach notification, and ethical considerations of transparency and accountability. Regular training and simulation exercises are crucial to ensure preparedness and effective execution of this framework. Question 4. Compliance review shows that the organization's cloud database environment has been experiencing performance degradation, and the database administrator is considering several options to address this. The primary concern is to maintain a strong security posture and meet regulatory requirements for data access and modification tracking. Which of the following approaches to database auditing represents the most professionally sound and compliant strategy? Option A. Disable all database auditing features to eliminate any potential performance overhead, relying solely on network-level logging for security monitoring. Option B. Implement a risk-based auditing strategy that focuses on monitoring sensitive data access, critical schema changes, and authentication events, while continuously evaluating and adjusting the scope based on evolving threats and compliance needs. Option C. Configure auditing to use only the default settings provided by the cloud database service, without any further customization or risk assessment. Option D. Enable auditing for every single database operation, including routine queries and read operations on non-sensitive data, to ensure maximum visibility. The correct answer is B. Implement a risk-based auditing strategy that focuses on monitoring sensitive data access, critical schema changes, and authentication events, while continuously evaluating and adjusting the scope based on evolving threats and compliance needs. Explanation: scenario analysis. This scenario presents a common challenge in cloud database environments where balancing robust security and auditing with operational efficiency is paramount. The challenge lies in identifying the most effective auditing strategy that meets regulatory compliance requirements without introducing undue performance overhead or complexity. A one-size-fits-all approach to auditing is rarely optimal, necessitating a risk-based methodology to prioritize what needs to be tracked. The professional must consider the sensitivity of the data, potential threats, and the specific compliance mandates applicable to the organization's industry and data handling practices. Correct approach analysis. Implementing a risk-based auditing strategy is the best professional practice. This approach involves identifying critical data assets and sensitive operations, then tailoring auditing controls to monitor these specific areas. For instance, auditing DDL data definition language changes, DML data manipulation language, operations on sensitive tables like PII or financial data, and authentication/authorization events provides granular visibility into potential security breaches or compliance violations. This method ensures that auditing efforts are focused on the highest risk activities, maximizing the effectiveness of security monitoring and incident response while minimizing performance impact. This aligns with the principle of least privilege and proportionate security controls, often implicitly or explicitly required by regulatory frameworks that mandate data protection and accountability. Incorrect approach is analysis. Auditing every single database operation without regard to risk is an inefficient and potentially detrimental approach. It generates an overwhelming volume of logs, making it difficult to identify genuine security incidents or compliance issues. This noise can lead to alert fatigue and increased storage and processing costs, without a proportional increase in security posture. From a regulatory perspective, this approach fails to demonstrate a targeted and risk-informed security strategy, which could be viewed as a deficiency in due diligence. Disabling all auditing to improve performance is a severe regulatory and ethical failure. It directly contravenes the principle of accountability and transparency in data handling. Many regulations require organizations to maintain audit trails for data access and modifications to ensure data integrity and to investigate potential misuse. Disabling auditing leaves the organization blind to critical activities, making it impossible to detect or respond to security incidents, comply with data breach notification requirements, or provide evidence for forensic investigations. This is a direct abdication of responsibility for data security and governance. Implementing auditing solely based on the default settings provided by the database system, without a specific risk assessment, is a suboptimal approach. While default settings may offer some level of auditing, they are often not tailored to the specific risks and compliance obligations of an organization. This can lead to gaps in coverage for critical data or operations, or excessive auditing of low-risk activities. It demonstrates a lack of proactive security planning and may not satisfy the demonstrably effective requirements of many compliance frameworks. Professional reasoning. Professionals should adopt a structured, risk-driven approach to database auditing. This involves 1. Identifying sensitive data and critical business processes. 2. Understanding applicable regulatory and compliance requirements. 3. Conducting a threat modeling exercise to identify potential attack vectors and insider threats. 4. Designing an auditing strategy that prioritizes monitoring of high-risk activities, including data access, modifications, administrative actions, and authentication events. 5. Regularly reviewing and refining the auditing strategy based on evolving threats, changes in data sensitivity, and new regulatory mandates. 6. Ensuring that audit logs are securely stored, retained for the required period, and regularly analyzed for suspicious activity. Question 5. During the evaluation of a critical production database outage on Google Cloud, a senior engineer proposes immediately granting broad administrative privileges to a temporary troubleshooting group and connecting directly to the database instance from their local machines to expedite diagnosis. Another team member suggests using the database's built-in diagnostic tools and cloud logging to analyze recent events and access logs, while also ensuring any necessary temporary access is granted via granular IAM roles with strict time limits and auditing enabled. A third suggestion is to bypass all security protocols and directly manipulate database files on the underlying storage to attempt a quick fix, which approach best adheres to professional best practices for database operations and compliance in a regulated environment. Option A. Immediately restarting the database instance without any prior investigation to see if the issue resolves itself. Option B. Utilizing the database's built-in diagnostic tools and cloud logging to analyze recent events and access logs, while also ensuring any necessary temporary access is granted via granular IAM roles with strict time limits and auditing enabled. Option C. Granting broad administrative privileges to a temporary troubleshooting group and connecting directly to the database instance from their local machines to expedite diagnosis. Option D. Bypassing all security protocols and directly manipulating database files on the underlying storage to attempt a quick fix. The correct answer is B. Utilizing the database's built-in diagnostic tools and cloud logging to analyze recent events and access logs, while also ensuring any necessary temporary access is granted via granular IAM roles with strict time limits and auditing enabled. Explanation. Scenario analysis. This scenario presents a common challenge in cloud database administration, balancing the need for rapid access and troubleshooting with the imperative of maintaining robust security and compliance. The pressure to resolve an outage quickly can lead to shortcuts that inadvertently compromise data integrity, access controls, or audit trails, all of which have significant regulatory implications. The professional challenge lies in identifying the root cause of the issue without introducing new vulnerabilities or violating established security policies and data governance frameworks. Correct approach analysis. The correct approach prioritizes a systematic, documented, and secure method for diagnosing and resolving the database issue. This involves leveraging the built-in monitoring and logging capabilities of Google Cloud, specifically cloud logging and cloud monitoring, to gather diagnostic information. Accessing the database for troubleshooting should be done through secure, audited channels, such as Cloud Shell or a Bastion host with strict IAM controls. Any changes made to the database configuration or data must be logged, and where applicable, approved through a change management process. This adherence to documented procedures and secure access aligns with best practices for operational resilience and data governance, ensuring that troubleshooting activities are traceable, auditable, and do not introduce security risks. This approach supports compliance with data protection regulations by maintaining the integrity of audit logs and access records. Incorrect approach is analysis. Granting broad administrative privileges to an ad hoc troubleshooting team without a clear scope, duration, or audit trail is a significant security and compliance failure. This bypasses established access control policies, increasing the risk of unauthorized data access or modification, which could violate data privacy regulations. Directly connecting to the database from an untrusted network or using unauthenticated credentials circumvents security protocols and creates an unacceptable risk of data breach. Such actions would likely violate internal security policies and potentially external regulatory requirements related to data security and access management. Attempting to resolve the issue by making undocumented, direct changes to the database files without proper change control or rollback procedures is also a critical failure. This introduces instability, makes future troubleshooting more difficult, and erodes the auditability of system changes, which is essential for compliance and incident response. It also increases the risk of data corruption or loss. Professional reasoning. Professionals should approach database incidents with a framework that prioritizes security, compliance, and systematic problem solving. This involves 1. Incident triage. Quickly assess the impact and scope of the issue. 2. Information gathering. Utilize approved monitoring and logging tools to collect data. 3. Secure access. Employ authenticated and authorized methods for accessing affected systems. 4. Root cause analysis. Systematically investigate the gathered data to identify the underlying problem. 5. Remediation. Implement solutions following established change management processes. 6. Verification. Confirm the issue is resolved and monitor for recurrence. 7. Documentation. Record all actions taken, findings, and resolutions for audit and future reference. This structured approach ensures that operational demands do not compromise security and compliance mandates. Question 6. Market research demonstrates that financial institutions are increasingly adopting cloud-native database solutions to enhance scalability and agility. A professional cloud database engineer is tasked with planning and executing an upgrade for a critical production PostgreSQL database running on Google Cloud Platform, which supports high-frequency trading operations. The primary concern is to minimize any potential disruption to trading activities and ensure compliance with financial regulations regarding data integrity and availability. Which of the following approaches best addresses the inherent risks associated with this database upgrade? Option A. Prioritize the fastest upgrade path to minimize downtime, relying on the vendor's default upgrade procedures and assuming minimal impact on trading operations. Option B. Implement the upgrade during a scheduled maintenance window without extensive pre-testing, assuming that Google Cloud's managed services will automatically handle any unforeseen issues. Option C. Conduct a comprehensive risk assessment, develop detailed rollback plans, perform extensive testing in a staging environment that mirrors production, and implement a phased rollout strategy with continuous monitoring. Option D. Focus solely on upgrading the database software to the latest version, deferring extensive testing and rollback planning to post-upgrade verification to save time and resources. The correct answer is C. Conduct a comprehensive risk assessment, develop detailed rollback plans, perform extensive testing in a staging environment that mirrors production, and implement a phased rollout strategy with continuous monitoring. Explanation. This scenario is professionally challenging because planning and executing database upgrades in a production environment, especially for a critical financial services application, carries significant risk. Downtime, data corruption, performance degradation, and security vulnerabilities are all potential consequences of a poorly managed upgrade. The need to balance business continuity with the adoption of new technology requires meticulous planning, thorough testing, and robust rollback strategies. Adherence to regulatory frameworks is paramount, as failures can lead to severe financial penalties, reputational damage, and loss of customer trust. The correct approach represents best professional practice because it prioritizes a comprehensive risk assessment and mitigation strategy. This aligns with industry best practices and regulatory expectations for managing critical IT infrastructure. By identifying potential failure points, developing contingency plans, and involving all relevant stakeholders, the team minimizes the likelihood of negative impacts. This proactive stance demonstrates due diligence and a commitment to maintaining the integrity and availability of the financial database, which is a core requirement for compliance in regulated industries. An incorrect approach that focuses solely on minimizing immediate cost without adequate risk assessment is professionally unacceptable. This could lead to overlooking critical testing phases or insufficient rollback planning, directly violating principles of responsible IT management, and potentially contravening regulatory requirements for system resilience and data integrity. For example, neglecting thorough performance testing under load could result in post-upgrade performance issues that impact transaction processing, a critical failure in a financial services context. Another incorrect approach that prioritizes speed over thoroughness, such as skipping staged rollouts or extensive user acceptance testing, is also professionally unsound. This haste increases the probability of unforeseen issues surfacing in production, which can have immediate and severe business consequences. Regulatory bodies often mandate that systems handling sensitive data must be stable and reliable, and a rushed upgrade process undermines this expectation. The professional decision-making process for similar situations should involve a structured risk management framework. This includes defining the scope and objectives of the upgrade, identifying all potential risks, technical, operational, security, compliance, assessing the likelihood and impact of each risk, developing mitigation strategies, establishing clear communication channels with stakeholders, and defining success criteria and rollback procedures. Continuous monitoring and validation throughout the upgrade process are also essential. Question 7. The monitoring system demonstrates a critical performance degradation impacting customer-facing applications, requiring immediate investigation into database logs and configuration files. The engineer suspects a recent configuration change might be the root cause, but accessing the specific sensitive customer data within the logs requires elevated privileges that are not part of their standard role. The established data governance policy mandates a formal request and approval process for accessing sensitive data, even for troubleshooting, with a defined emergency exception procedure that involves notifying the Data Governance Officer and the Security Operations Center, SOC, before proceeding with temporary, audited access. Which of the following actions best adheres to the principles of data governance and regulatory compliance in this scenario? Option A. Immediately access the sensitive log data using existing administrative credentials, document the access for later review, and inform the Data Governance Officer and SOC after the issue is resolved. Option B. Initiate the formal emergency exception process by notifying the Data Governance Officer and SOC, clearly stating the business justification and the specific data required, and await their documented approval before accessing the sensitive log data. Option C. Access all available database logs and configuration files indiscriminately to gather as much information as possible, hoping to find the cause without needing specific authorization for sensitive data. Option D. Proceed with accessing the sensitive log data without formal notification or approval, assuming the urgency of the situation overrides the standard governance procedures, and address any compliance concerns retrospectively. The correct answer is A. Immediately access the sensitive log data using existing administrative credentials, document the access for later review, and inform the Data Governance Officer and SOC after the issue is resolved. Explanation. This scenario presents a professional challenge because it requires balancing the immediate need for data access to resolve a critical system issue with the long-term imperative of adhering to established data governance policies. The tension lies between operational urgency and regulatory compliance, demanding a decision that minimizes risk while addressing the immediate problem. The correct approach represents best professional practice because it prioritizes a structured, documented, and authorized process for accessing sensitive data, even in an emergency. This aligns with the principles of data governance, which mandate that access to data, especially sensitive or regulated data, must be controlled, audited, and justified. By following the established exception process, the engineer ensures that the access is recorded, reviewed, and compliant with any relevant data privacy regulations, e.g., GDPR if applicable to the data's origin, or specific U.S. federal/state regulations like HIPAA for health data, or CCPA for California consumer data, depending on the context of the data being governed. This approach maintains data integrity, accountability, and trust, which are foundational to effective data governance. An incorrect approach that bypasses established procedures for data access, even with good intentions, creates significant regulatory and ethical failures. It undermines the integrity of the data governance framework, making it difficult to audit data access and potentially leading to unauthorized disclosure or misuse of sensitive information. This could result in violations of data privacy laws, leading to substantial fines, reputational damage, and loss of customer trust. For instance, accessing personally identifiable information, PI, without proper authorization or logging could violate regulations like GDPR or CCPA, which require strict controls over PII. Similarly, accessing protected health information, FI, without adhering to HIPAA protocols would be a severe breach. Ethically, it demonstrates a disregard for established controls designed to protect individuals' data. Another incorrect approach that involves broad, indiscriminate access to data, rather than targeted access for the specific issue, is also professionally unacceptable. This broad access increases the risk of accidental exposure or misuse of data beyond what is necessary to resolve the problem, further exacerbating regulatory and ethical concerns. It fails to uphold the principle of data minimization, a key tenet of many data governance frameworks and privacy regulations. The professional reasoning process for similar situations should involve 1. Assess the urgency and impact. Clearly define the criticality of the issue and the potential consequences of inaction. 2. Consult governance policies. Immediately refer to the organization's data governance policies and procedures, including any defined emergency access protocols or exception handling. 3. Identify authorized pathways. Determine the officially sanctioned methods for obtaining necessary data access, even under duress. This might involve escalating to a data governance committee, security operations, or a designated data steward. 4. Document everything. Meticulously record all actions taken, justifications for any deviations from standard procedure, and communications with relevant stakeholders. 5. Seek authorization. Obtain explicit authorization for any data access that falls outside standard operating procedures, ensuring it is documented. 6. Minimize data exposure. If emergency access is granted, ensure it is limited to the absolute minimum data required to resolve the issue and is performed in a secure, auditable manner. 7. Post-incident review. Conduct a thorough review after the incident to identify any gaps in the governance framework and implement improvements. Question 8. Regulatory review indicates that a global financial services firm is migrating its core trading platform to Google Cloud, requiring a database solution that offers strong global consistency, high availability, and low latency for users across North America, Europe, and Asia. The firm's compliance department has emphasized the need for a database that can guarantee transactional integrity across all regions without compromising performance. The engineering team is considering how to best leverage Cloud Spanner for this critical application. Which of the following approaches best meets the firm's requirements for global scalability, strong consistency, and schema design considerations within Cloud Spanner? Option A. Deploy Cloud Spanner in a single region configuration within North America to minimize latency for the largest user base and implement application-level logic for eventual consistency across other regions. Option B. Deploy Cloud Spanner in a multi-region configuration, but prioritize a schema that uses sharding based on user location to achieve perceived scalability, accepting potential inconsistencies during shard rebalancing. Option C. Deploy Cloud Spanner in a multi-region configuration and design a schema that relies heavily on complex cross-region joins to retrieve all necessary trading data for each transaction. Option D. Deploy Cloud Spanner in a multi-region configuration that spans North America, Europe, and Asia, and design the schema to utilize Spanner's global secondary indexes and avoid cross-region joins for critical transaction paths. The correct answer is D. Deploy Cloud Spanner in a multi-region configuration that spans North America, Europe, and Asia, and design the schema to utilize Spanner's global secondary indexes and avoid cross-region joins for critical transaction paths. Explanation. This scenario presents a professional challenge due to the critical need to balance global application availability with stringent data consistency requirements, a common dilemma when designing distributed databases. The professional cloud database engineer must navigate the inherent trade-offs between latency, consistency, and scalability, ensuring compliance with the implicit regulatory expectation of data integrity and availability for a global financial services application. Careful judgment is required to select a Cloud Spanner configuration that meets both functional and non-functional requirements without compromising user experience or regulatory adherence. The correct approach represents best professional practice because it directly addresses the core requirements of strong consistency and global scalability inherent to Cloud Spanner. By selecting a multi-region configuration, the engineer ensures that data is replicated across geographically dispersed regions, providing high availability and low latency for users worldwide. The choice of a schema that leverages Spanner's global indexing capabilities and avoids overly complex joins across regions minimizes query latency and maximizes performance, aligning with the regulatory expectation of reliable and accessible financial data. This proactive design minimizes the risk of data inconsistencies and ensures that the application can scale to meet future demand while maintaining its integrity. An incorrect approach that prioritizes a single region deployment for perceived cost savings or simplicity would fail to meet the global availability requirement, leading to potential downtime and data access issues for users in other regions. This directly contravenes the implicit regulatory expectation of continuous service availability for financial transactions. Another incorrect approach that neglects schema optimization, leading to inefficient queries and high latency, would also be professionally unacceptable. Such inefficiency could result in delayed transactions, impacting user trust and potentially violating service-level agreements, which are often subject to regulatory oversight. Furthermore, choosing a schema that does not leverage Spanner's strong consistency guarantees, perhaps by attempting to implement eventual consistency patterns within Spanner, would fundamentally misunderstand the platform's strengths and introduce unnecessary complexity and risk of data divergence, a critical failure in a financial context. The professional decision-making process should involve a thorough understanding of the application's global reach, its data consistency needs, and the specific capabilities of Cloud Spanner. Engineers should prioritize solutions that inherently support strong consistency and global distribution, then focus on optimizing schema design for performance within those constraints. This involves evaluating the trade-offs of different Spanner configurations and schema patterns against business requirements and regulatory expectations for data integrity and availability. Question 9. The audit findings indicate a potential exposure of sensitive customer information in non-production environments, raising concerns about compliance with data privacy regulations. As a professional cloud database engineer, what is the most effective strategy to implement robust data masking for enhanced data privacy while ensuring data utility for development and testing purposes? Option A. Encrypt all sensitive data fields in the production database and provide decryption keys to development and testing teams as needed. Option B. Create a separate, static copy of the production database for development and testing, applying deterministic masking techniques to all sensitive fields in this copied dataset. Option C. Implement dynamic data masking at the database level, applying masking rules based on user roles and permissions, and supplement with tokenization for highly sensitive fields where appropriate. Option D. Rely exclusively on application-level masking logic to obscure sensitive data before it is displayed or processed by development and testing tools. Correct answer is C. Implement dynamic data masking at the database level, applying masking rules based on user roles and permissions, and supplement with tokenization for highly sensitive fields where appropriate. Explanation. This scenario presents a common challenge in cloud database management, balancing data utility for development and testing with stringent data privacy requirements. The audit findings highlight a potential compliance gap, necessitating a robust data masking strategy. The professional challenge lies in selecting a masking technique that effectively protects sensitive data without rendering it unusable for critical downstream processes, all while adhering to relevant regulations. The correct approach represents best professional practice because it prioritizes a comprehensive, context-aware masking strategy. By implementing dynamic data masking at the database level, sensitive data is masked in real time for unauthorized users, ensuring compliance with data privacy regulations such as GDPR or CCPA, depending on the exam's specified jurisdiction, which for this exam is assumed to be US-centric for data privacy principles. This method allows authorized users to access the original data when necessary, maintaining data integrity for production operations. Furthermore, employing a combination of masking techniques tailored to specific data types and use cases demonstrates a mature understanding of data governance and risk management. This proactive and layered approach minimizes the risk of data breaches and regulatory penalties, fostering trust and maintaining operational efficiency. An incorrect approach that involves static data masking by creating a separate, masked copy for development environments is professionally unacceptable. While it masks data, it creates an additional data silo, increasing management overhead and the risk of inconsistencies between production and non-production environments. This can lead to errors in development and testing, potentially causing compliance issues if masked data is inadvertently used in production or if the masking process itself is flawed. It also fails to address real-time access needs for authorized personnel in production. Another incorrect approach, relying solely on application-level masking, is also professionally deficient. This method is often less secure and more prone to errors, as it depends on the correct implementation of masking logic within each application. A single oversight or vulnerability in an application could expose sensitive data, It also lacks the centralized control and consistent enforcement that database-level masking provides, making it harder to audit and maintain compliance across the entire data landscape. This fragmented approach increases the likelihood of regulatory noncompliance and data privacy violations. The professional decision-making process for such situations should involve a thorough risk assessment of sensitive data, identification of all data consumers and their access requirements, and an evaluation of various masking techniques against these needs and regulatory mandates. Prioritizing solutions that offer granular control, real-time masking capabilities, and ease of auditing is crucial. Collaboration with legal, compliance, and development teams is essential to ensure that the chosen masking strategy meets both technical and regulatory objectives. Question 10. Cost-benefit analysis shows that a rapid migration of sensitive customer data from an on-premises SQL server to Cloud SQL for PostgreSQL is a high priority. The data includes personally identifiable information, PI, that is subject to strict U.S. data privacy regulations. The engineering team is considering several import strategies to meet the aggressive timeline. Which strategy best balances speed, cost, and regulatory compliance for this scenario? Option A. Utilizing Google Cloud's Database Migration Service, DMS, with its built-in encryption for data in transit and at rest, configured to perform a continuous replication or a one-time dump and load, ensuring all data is encrypted throughout the process. Option B. Exporting the data to encrypted JSON files on the on-premises server, then uploading these files to a publicly accessible Google Cloud storage bucket via HTTP, and finally importing them into Cloud SQL. Option C. Manually scripting a custom data extraction process that bypasses standard database export tools, sending the raw data directly over a non-encrypted network connection to a temporary instance for processing before loading into Cloud SQL. Option D. Exporting the data from the on-premises SQL server to unencrypted CSV files, transferring these files to a Google Cloud storage bucket using standard FTP, and then using the Cloud SQL import utility to load the CSV data. The correct answer is D. Exporting the data from the on-premises SQL server to unencrypted CSV files, transferring these files to a Google Cloud storage bucket using standard FTP, and then using the Cloud SQL import utility to load the CSV data. Explanation. This scenario is professionally challenging because it requires balancing the efficiency of data migration with stringent regulatory compliance, specifically concerning data privacy and security during transit and at rest. The chosen method for importing data must not only be technically sound, but also adhere to the principles of data protection as mandated by relevant U.S. regulations, such as HIPAA for healthcare data or GDPR-like principles if handling data of EU citizens. Even within a U.S. context, the professional must ensure that the chosen import method minimizes the risk of unauthorized access, data leakage, or corruption, all while meeting business objectives for timely data availability. The correct approach represents best professional practice because it prioritizes security and compliance by utilizing Google Cloud's native, encrypted import mechanisms. Services like cloud storage with server-side encryption, combined with secure transfer protocols, e.g., HTTPS for direct uploads or secure connections for tools like G Sudo, ensure that data is protected both in transit and at rest. This aligns with the principle of security by design and privacy by design, which are fundamental to U.S. data protection laws. By leveraging these built-in security features, the engineer demonstrates due diligence in safeguarding sensitive information, thereby mitigating legal and reputational risks. An incorrect approach that involves exporting data to unencrypted CSV files and then uploading them via standard FTP would represent a significant regulatory and ethical failure. FTP is an inherently insecure protocol that transmits data in plain text, exposing it to interception and unauthorized access. This directly violates the confidentiality requirements of most data protection regulations. Similarly, importing data using a method that bypasses standard access controls or logging mechanisms would hinder auditability and accountability, making it impossible to demonstrate compliance with data governance policies and regulatory mandates. Such an approach would be considered negligent and could lead to severe penalties, including fines and legal action, due to data breaches. Professionals should approach such decisions by first identifying the sensitivity and regulatory classification of the data to be imported. This dictates the required security controls. Next, they should evaluate available Google Cloud services and tools, prioritizing those that offer robust encryption, access control, and auditing capabilities. A risk assessment should be performed for each potential method, considering threats like man-in-the-middle attacks, unauthorized access to storage, and data exfiltration. The decision should be documented, including the rationale for selecting a particular method and the security measures implemented, to ensure transparency and facilitate future audits. Question 11. Implementation of a new customer relationship management (CRM) database on Google Cloud requires adherence to stringent data privacy and financial transaction logging regulations. The engineering team needs to ensure that sensitive customer PII and all financial transaction details are protected, accessible only to authorized personnel, and that a complete audit trail of all data access and modifications is maintained. Which of the following approaches best ensures compliance with these regulatory requirements? Option A. Implement a strong network firewall at the edge of the Google Cloud VPC and grant broad read/write access to the database for all internal application services. Option B. Rely on the default security settings provided by Google Cloud for the database service and assume that application-level security is sufficient. Option C. Encrypt only the data that is explicitly marked as sensitive by the application and disable detailed logging to reduce storage costs. Option D. Configure granular identity and access management (IAM) roles for database access, enforce encryption at rest and in transit for all data, and enable comprehensive cloud audit logs for database operations. The correct answer is D. Configure granular identity and access management (IAM) roles for database access, enforce encryption at rest and in transit for all data, and enable comprehensive cloud audit logs for database operations. Explanation. The scenario presents a common challenge in cloud database engineering, balancing the need for robust data security and privacy with the operational requirements of a growing business. The professional challenge lies in interpreting and applying complex regulatory frameworks, such as those governing data protection and financial services, to a dynamic cloud environment. This requires not just technical expertise, but also a deep understanding of legal and compliance obligations, ensuring that technical solutions directly address regulatory mandates without introducing new risks. The correct approach represents best professional practice because it proactively embeds compliance into the database architecture and operational processes. By leveraging Google Cloud's native security and auditing features, and by implementing granular access controls and encryption, the solution directly addresses the core requirements of data protection regulations. This aligns with the principle of privacy by design and security by design, which are fundamental to ethical and compliant data handling. Specifically, using IAM for least privilege access, cloud audit logs for accountability, and encryption at rest and in transit directly mitigates risks of unauthorized access and data breaches, fulfilling regulatory obligations to protect sensitive information. An incorrect approach that relies solely on perimeter security fails to meet regulatory standards because it assumes a static threat model and overlooks the dynamic nature of cloud environments and insider threats. Regulations often mandate defense-in-depth strategies, which include robust access controls and data-level protection, not just network-level security. Another incorrect approach that prioritizes ease of access over granular control is professionally unacceptable due to significant regulatory and ethical failures. Broad access permissions increase the likelihood of accidental or malicious data exposure, violating data protection principles, and potentially leading to severe penalties under regulations like GDPR or CCPA, if applicable to the exam's jurisdiction. This demonstrates a disregard for the principle of least privilege, a cornerstone of secure and compliant database management. A third incorrect approach that neglects regular auditing and monitoring creates blind spots in the security posture. Compliance regulations often require demonstrable evidence of security controls and data access. The absence of comprehensive audit trails makes it impossible to prove compliance, investigate incidents effectively, or identify policy violations, thereby failing to meet accountability and transparency requirements. The professional decision-making process for similar situations should involve a thorough risk assessment that considers regulatory requirements, business needs, and technical capabilities. This should be followed by a design phase that prioritizes security and compliance from the outset, incorporating principles like least privilege, encryption, and comprehensive auditing. Continuous monitoring, regular reviews, and adaptation to evolving threats and regulations are crucial for maintaining a compliant and secure database environment. Question 12. The evaluation methodology shows a scenario where a team is tasked with deploying a new set of production databases on Google Cloud Platform using infrastructure as code. They are considering different strategies for managing the database infrastructure, with a strong emphasis on adhering to internal security policies and external data protection regulations. Which of the following approaches best aligns with professional best practices for managing database infrastructure as code in a regulated environment? Option A. Utilize generic ISC templates for database provisioning and rely on post-deployment manual reviews to identify and correct any security or compliance deviations. Option B. Create ISC scripts for database provisioning without implementing version control or regular auditing of the scripts themselves, assuming that the cloud provider's default security settings are sufficient. Option C. Develop ISC templates that define database instances, including network configurations, encryption settings, access control lists, and auditing configurations, and integrate these templates into a CI/CD pipeline for automated deployment and validation against security policies. Option D. Provision database instances using ISC templates and then manually apply all security configurations, including firewall rules, user permissions, and audit logging, to ensure compliance with regulations. The correct answer is C. Develop ISC templates that define database instances, including network configurations, encryption settings, access control lists, and auditing configurations, and integrate these templates into a CI/CD pipeline for automated deployment and validation against security policies. Explanation. The evaluation methodology shows a common challenge in cloud database engineering, balancing rapid deployment and infrastructure consistency with robust security and compliance requirements. The professional challenge lies in selecting an infrastructure as code (ISC) strategy that not only automates database provisioning, but also embeds security controls and adheres to data governance policies from the outset, preventing costly remediation later. The correct approach represents best professional practice because it integrates security and compliance directly into the ISC pipeline. By defining database configurations, access controls, and auditing mechanisms as code, it ensures that every deployed database instance conforms to predefined security baselines and regulatory mandates. This declarative approach promotes immutability, reduces drift, and allows for automated security reviews and compliance checks within the CI/CD process, aligning with principles of secure development and operational excellence. An incorrect approach that relies solely on manual security configuration post-provisioning is professionally unacceptable. This method introduces significant regulatory and ethical failures by creating a window of vulnerability where databases may be deployed without necessary security hardening or compliance checks. It increases the risk of data breaches, unauthorized access, and noncompliance with data protection regulations, leading to potential legal penalties and reputational damage. Another incorrect approach that uses generic, nonspecific ISC templates without tailoring them to specific security and compliance needs fails to address the unique risks associated with sensitive data. This can lead to overpermissive configurations or the omission of critical security controls, violating the principle of least privilege and potentially contravening data residency or privacy laws. A third incorrect approach that neglects version control and auditing for ISC scripts introduces risks of unauthorized changes and lack of accountability. Without proper versioning, it becomes difficult to track who made what changes, when, and why, hindering incident response and auditability, which are fundamental to regulatory compliance and ethical data stewardship. Professionals should adopt a decision-making framework that prioritizes security and compliance by design. This involves selecting ISC tools and methodologies that support policy as code, integrating security scanning and compliance checks into the CI/CD pipeline, and ensuring that all infrastructure definitions are version-controlled, peer-reviewed, and regularly audited. The focus should always be on automating secure and compliant deployments, rather than relying on manual interventions that are prone to error and oversight. Question 13. Strategic planning requires a thorough understanding of database concurrency control mechanisms to ensure optimal performance and data integrity. A large e-commerce platform running on Google Cloud is experiencing significant transaction volume and requires a concurrency control strategy that maximizes throughput while maintaining strong data consistency for order processing and inventory management. The engineering team is evaluating different approaches. Which of the following strategies best addresses these requirements in a distributed database environment? Option A. Implement optimistic concurrency control with versioning to detect and resolve conflicts at commit time. Option B. Adopt a distributed locking mechanism that serializes all write operations across all nodes. Option C. Utilize a simple first-come, first-served FCFS transaction ordering without explicit conflict detection. Option D. Employ pessimistic concurrency control using strict two-phase locking 2PL to prevent conflicts before they occur. Correct answer is A. Implement optimistic concurrency control with versioning to detect and resolve conflicts at commit time. Explanation. Scenario analysis. This scenario is professionally challenging because it involves balancing high transaction throughput with data consistency requirements in a distributed database environment. The professional cloud database engineer must select a concurrency control mechanism that minimizes performance degradation while adhering to data integrity principles, which are implicitly governed by general data protection and privacy regulations that mandate accurate and reliable data. Failure to select an appropriate mechanism can lead to data corruption, incorrect reporting, and potential breaches of trust, which could have regulatory implications if sensitive data is involved. Correct approach analysis. Implementing optimistic concurrency control with versioning is the best professional practice in this scenario. This approach allows transactions to proceed without acquiring locks, significantly improving throughput and reducing contention, especially in read-heavy workloads or when conflicts are infrequent. Versioning allows the system to detect conflicts at commit time and roll back only the conflicting transaction, rather than blocking multiple transactions. This aligns with the principle of efficient resource utilization and maintaining data availability, which are indirectly supported by regulations that encourage robust and reliable systems for data processing. Incorrect approaches analysis. Choosing pessimistic concurrency control with strict two-phase locking 2PL would be a regulatory and ethical failure. While it guarantees serializability, it can lead to significant performance bottlenecks and deadlocks, especially under high load. This inefficiency could indirectly violate principles of responsible data stewardship by hindering timely access to accurate information. Ethically, it represents an over-reliance on a mechanism that prioritizes absolute consistency at the expense of usability and performance, potentially impacting business operations that rely on timely data. Implementing a simple first-come, first-served FCFS ordering without explicit conflict detection or resolution would be a critical failure. This approach offers no guarantee of data consistency and would almost certainly lead to lost updates and corrupted data. This directly contravenes the fundamental ethical and regulatory obligation to maintain data integrity and accuracy, especially if the data is used for decision-making or compliance purposes. Using a distributed locking mechanism that is not carefully designed for fault tolerance and performance would also be problematic. While it attempts to manage concurrency, a poorly implemented distributed lock can become a single point of failure or a performance bottleneck, similar to pessimistic locking. This could lead to system instability and unreliable data access, indirectly impacting compliance with regulations that require system availability and data integrity. Professional reasoning. Professionals should employ a decision-making framework that starts with understanding the workload characteristics, read vs. write ratio, transaction complexity, expected contention. Then, they should evaluate concurrency control mechanisms against these characteristics, considering their impact on throughput, latency, consistency guarantees, and complexity of implementation and management. The chosen mechanism must align with the business's tolerance for data staleness versus its need for high availability and performance, always keeping in mind the implicit requirement for data integrity mandated by general data protection principles. Question 14. The assessment process reveals that a critical production database requires a robust solution for high availability and disaster recovery to meet stringent business continuity objectives. The current infrastructure relies on a single instance, posing a significant risk. The engineering team is evaluating different replication strategies to ensure minimal data loss and rapid recovery in the event of an outage or regional failure. Which of the following approaches best aligns with professional best practices for implementing and managing database replication for high availability and disaster recovery in a Google Cloud environment, considering regulatory compliance and operational efficiency? Option A. Develop and deploy custom replication scripts that manually synchronize data between instances in different regions, with ad hoc monitoring and manual failover procedures. Option B. Implement a managed cross-region replication service provided by Google Cloud, configured to meet the defined RTO/RPO targets and leverage automated failover mechanisms. Option C. Utilize a single region replication setup with asynchronous replication to reduce latency, assuming that regional failures are highly improbable. Option D. Prioritize the most cost-effective replication solution, even if it means accepting a higher RPO and a longer RTO, to minimize cloud infrastructure expenses. The correct answer is B. Implement a managed cross-region replication service provided by Google Cloud, configured to meet the defined RTO/RPO targets and leverage automated failover mechanisms. Explanation. The assessment process reveals a common challenge in cloud database engineering, balancing the need for robust high availability (HA) and disaster recovery (DR) with the operational complexities and cost implications of replication. Specifically, implementing and managing database replication requires a deep understanding of the chosen cloud provider's services, potential failure modes, and the specific business RTO/RPO, recovery time, objective/recovery point objective, requirements. The professional challenge lies in selecting the most appropriate replication strategy that meets these objectives without introducing unnecessary complexity or incurring excessive costs, while also adhering to any relevant data residency and compliance regulations. The correct approach represents best professional practice because it directly addresses the core requirements of HA and DR through a well-understood and supported cloud-native replication mechanism. This approach prioritizes the business's need for minimal downtime and data loss by leveraging a solution designed for resilience and failover. It also demonstrates a proactive understanding of potential network disruptions or instance failures, ensuring business continuity. From a regulatory perspective, using a managed service often simplifies compliance by providing built-in security features and audit trails, which are crucial for data protection and governance. An incorrect approach that relies on manual, custom replication scripts is professionally unacceptable due to several regulatory and ethical failures. Firstly, it introduces significant operational risk. Custom scripts are prone to errors, lack robust error handling, and are difficult to maintain and test, potentially leading to data inconsistencies or replication failures that violate data integrity principles. This can have severe compliance implications if data loss or corruption occurs, especially in regulated industries. Secondly, it bypasses the managed security and compliance features offered by cloud providers, potentially exposing sensitive data or failing to meet data residency requirements. Ethically, it demonstrates a lack of due diligence in selecting a reliable and secure solution, potentially jeopardizing client data and trust. Another incorrect approach that focuses solely on cost reduction without considering RTO/RPO objectives is also professionally unsound. While cost efficiency is important, it cannot come at the expense of business continuity. Failing to meet RTO/RPO targets can result in significant financial losses for the business, reputational damage, and potential regulatory penalties for non-compliance with service-level agreements or industry-specific regulations. This approach prioritizes a single metric over the holistic needs of the business and its stakeholders. The professional reasoning framework for such situations involves a systematic evaluation of requirements, available solutions, and associated risks. Professionals should start by clearly defining RTO/RPO objectives in collaboration with business stakeholders. Then, they should research and evaluate cloud-native replication services, considering their features, scalability, cost, and manage security. A thorough risk assessment should be conducted for each potential solution, including failure scenarios and mitigation strategies. Finally, the chosen solution should be documented, tested rigorously, and monitored continuously to ensure ongoing effectiveness and compliance. Question 15. Investigation of a Cloud SQL for SQL Server instance reveals performance degradation during peak hours. The database engineer is tasked with optimizing query execution times for a critical application that handles sensitive customer financial data. The engineer considers several approaches to improve performance. Which approach best aligns with professional best practices for managing sensitive data in a cloud database environment? Option A. Apply aggressive query hints to all critical queries to force specific execution plans, assuming this will always yield the fastest results, and defer any security reviews until after the performance issues are resolved. Option B. Implement a comprehensive set of new indexes across all tables, focusing on columns frequently used in where clauses, without prior analysis of query execution plans or data access patterns. Option C. Establish a performance baseline, analyze current query execution plans, identify specific bottlenecks, and then incrementally implement targeted optimizations, such as adding specific indexes or adjusting query logic, while continuously monitoring performance and security logs. Option D. Immediately disable all auditing and logging features to reduce overhead and improve query throughput, as these are known to impact performance. The correct answer is B. Implement a comprehensive set of new indexes across all tables, focusing on columns frequently used in where clauses, without prior analysis of query execution plans or data access patterns. Explanation. This scenario presents a professional challenge due to the inherent tension between performance optimization and data security/compliance requirements within a regulated cloud environment. The database engineer must balance the need for rapid query execution with the imperative to protect sensitive customer data, as mandated by industry, best practices, and potential regulatory frameworks governing data handling. Careful judgment is required to ensure that any performance tuning does not inadvertently compromise data integrity or expose it to unauthorized access. The correct approach represents best professional practice because it prioritizes a systematic, data-driven, and compliant method for performance tuning. By first establishing a baseline, then implementing changes incrementally and monitoring their impact, the engineer ensures that optimizations are effective and do not introduce regressions or security vulnerabilities. This methodical approach aligns with principles of responsible data management and IT governance, which are often implicitly or explicitly required by industry standards and ethical codes of conduct for IT professionals. It demonstrates a commitment to maintaining system stability and data security while pursuing efficiency. An incorrect approach that involves immediately applying aggressive indexing strategies without understanding the data's access patterns or potential security implications is professionally unacceptable. This could lead to over-indexing, which can degrade write performance and increase storage costs, and more critically, might inadvertently expose sensitive data if indexing strategies are not carefully designed with security in mind. Such a hasty action bypasses essential diagnostic steps and risk assessment, violating the principle of due diligence in managing critical IT systems. Another incorrect approach, such as disabling security features to improve query speed, represents a severe ethical and professional failure. Security features are in place to protect data from unauthorized access, modification, or disclosure. Disabling them, even temporarily, for performance gains directly contravenes the responsibility to safeguard data and uphold trust. This action would likely violate data protection regulations and industry standards, exposing the organization to significant legal and reputational risks. The professional reasoning process for similar situations should involve a structured approach. 1. Understand the requirements. Clearly define performance goals and any associated security or compliance constraints. 2. Baseline assessment. Establish current performance metrics and identify specific bottlenecks. 3. Risk assessment. Evaluate potential impacts of any proposed changes on data security, integrity, and compliance. 4. Incremental implementation. Apply changes one at a time, thoroughly testing each modification. 5. Continuous monitoring. Track performance, resource utilization, and security logs after each change. 6. Documentation. Maintain detailed records of all changes, their rationale, and their observed effects. 7. Stakeholder communication. Keep relevant parties informed of progress and any potential issues. Question 16. What factors determine the optimal combination of Google Cloud Platform, GCP core services, including compute engine, networking, storage, and identity and access management (EM), for deploying a production-grade relational database, considering performance, security, and manageability? Option A. The lowest cost storage solution available on GCP, regardless of its suitability for database operations or performance implications. Option B. The most recently released GCP service, assuming it offers superior performance and features without further investigation. Option C. The default network configuration provided by GCP without considering specific security group rules or firewall policies. Option D. The specific database engine requirements, the need for managed versus self-managed services, the organization's security posture and compliance needs, and the desired level of operational overhead. The correct answer is D. The specific database engine requirements, the need for managed versus self-managed services, the organization's security posture and compliance needs, and the desired level of operational overhead. Explanation. This scenario is professionally challenging because it requires balancing the immediate need for rapid deployment of a critical database with the long-term implications of security, compliance, and cost efficiency within the Google Cloud Platform, GCP, ecosystem. A database engineer must not only understand the technical capabilities of GCP services, but also how they align with organizational policies and potential regulatory requirements, even if not explicitly stated in the prompt, as best practice dictates anticipating such needs. The correct approach represents best professional practice because it prioritizes a foundational understanding of GCP's core services and their interdependencies. Selecting Compute Engine for the database server, Cloud SQL for managed database services, and cloud storage for backups demonstrates an awareness of GCP's tiered service offerings and their respective strengths. This approach acknowledges that different services are optimized for different purposes, leading to a more robust, secure, and cost-effective solution. Specifically, using Compute Engine for a self-managed database requires careful consideration of patching, scaling, and security, while Cloud SQL abstracts much of this away, offering managed security, backups, and high availability. Cloud storage provides a reliable and scalable solution for backups, a critical component of data integrity and disaster recovery. This layered approach aligns with industry best practices for database deployment and management, ensuring data availability, durability, and security. An incorrect approach that focuses solely on the cheapest storage option, without considering the compute or database management aspects, would be a regulatory and ethical failure. This is because it neglects the fundamental requirements for running a database, such as processing power and reliable database software. Such an approach could lead to performance issues, data corruption, or security vulnerabilities, which could have severe consequences for the organization and its users, potentially violating data protection principles and service-level agreements. Another incorrect approach that might involve deploying a database directly onto a general-purpose virtual machine without considering managed database services like Cloud SQL would be a failure in professional decision-making. While technically feasible, it bypasses GCP's built-in security, patching, and high availability features, increasing the operational burden and risk of misconfiguration. This oversight could lead to non-compliance with internal security policies or industry standards for data handling, representing a failure to apply due diligence. A professional decision-making process for similar situations should involve a thorough assessment of the database's requirements, performance, availability, security, compliance, an evaluation of available GCP services that meet these requirements, and a consideration of the trade-offs between managed and self-managed solutions. It also necessitates understanding the organization's risk tolerance, budget, and operational capabilities. Prioritizing a holistic view of the solution, rather than focusing on a single component or cost-saving measure, is crucial for building resilient and compliant cloud database solutions. Question 17. When evaluating database performance tuning methodologies for a critical Google Cloud SQL instance experiencing intermittent slowdowns, which approach best aligns with professional best practices and ensures a systematic, data-driven resolution? Option A. Conduct a comprehensive analysis of query execution plans, identify slow-running queries, and optimize indexing strategies based on observed query patterns and workload analysis. Option B. Proactively increase the machine type and storage IOPS of the Cloud SQL instance to a significantly higher tier, assuming increased resources will resolve all performance issues. Option C. Focus solely on optimizing application-level caching mechanisms without investigating the database's internal performance metrics or query efficiency. Option D. Implement a series of random configuration parameter changes across the database server and operating system, hoping to stumble upon a beneficial adjustment. The correct answer is B. Proactively increase the machine type and storage IOPS of the Cloud SQL instance to a significantly higher tier, assuming increased resources will resolve all performance issues. Explanation. This scenario presents a common challenge for cloud database engineers, optimizing performance under varying workloads and resource constraints while adhering to best practices and potential regulatory considerations for data handling and availability. The professional challenge lies in balancing immediate performance gains with long-term maintainability, cost-effectiveness, and the integrity of the data. Careful judgment is required to select tuning methodologies that are not only effective, but also sustainable and compliant. The correct approach represents best professional practice because it adopts a systematic, data-driven methodology. This involves understanding the application's behavior, identifying bottlenecks through comprehensive monitoring, and then applying targeted tuning techniques. This iterative process ensures that changes are validated and that the root cause of performance issues is addressed, rather than just symptoms. In the context of Google Cloud, this aligns with best practices for managing cloud resources efficiently and reliably, which indirectly supports compliance with service-level agreements, SLAs, and data availability requirements that might be stipulated by industry regulations or contractual obligations. The focus on understanding query patterns and indexing strategies directly impacts database efficiency, which is a core tenet of professional database engineering. An incorrect approach that focuses solely on increasing hardware resources without diagnosing the underlying performance issues is professionally unacceptable. This is because it represents a brute force solution that is often cost inefficient and may not resolve the actual bottleneck. From a regulatory or ethical standpoint, such an approach could lead to unnecessary expenditure, which might be scrutinized in environments with strict budget controls or where resource utilization is audited. Furthermore, it fails to demonstrate due diligence in understanding the system's behavior, potentially leading to recurring issues or the masking of deeper architectural problems. Another incorrect approach that involves making broad, untested configuration changes without a clear hypothesis or baseline is also professionally unacceptable. This shotgun approach increases the risk of introducing new performance regressions or destabilizing the database. Ethically, it demonstrates a lack of rigor and a disregard for the potential impact on system availability and data integrity. Such actions could violate professional standards of care and potentially lead to breaches of service commitments or data access issues, which could have regulatory implications depending on the data's sensitivity and the industry. A professional decision-making process for similar situations should begin with a thorough understanding of the application's workload and performance requirements. This involves establishing baseline metrics through robust monitoring tools. Next, potential bottlenecks should be identified using diagnostic tools that analyze query execution plans, resource utilization, CPU, memory, I/O, and network latency. Based on this analysis, specific, testable hypotheses for performance improvements should be formulated. Tuning methodologies should then be applied incrementally, with each change being measured against the established baseline to assess its impact. This iterative, evidence-based approach ensures that optimizations are effective, efficient, and sustainable, while minimizing the risk of negative side effects. Question 18. The risk matrix shows a high probability of performance degradation impacting critical business operations within the next quarter for a large e-commerce platform utilizing Cloud Spanner for its order processing. The current infrastructure is experiencing intermittent query latency spikes, leading to user complaints and potential revenue loss. The engineering team needs to implement a strategy to mitigate these risks and ensure consistent performance. Option A. Conduct a comprehensive performance analysis, including query execution plan reviews, spanner metrics examination, and workload characterization, to identify specific bottlenecks. Based on these findings, optimize inefficient queries, ensure appropriate indexing, and reevaluate the current node count and configuration for optimal resource allocation. Option B. Focus exclusively on rewriting all existing application code that interacts with Cloud Spanner to implement more efficient data access patterns, without initially analyzing current query performance or resource utilization. Option C. Implement aggressive caching strategies at the application layer for all frequently accessed data in Cloud Spanner, assuming that the database itself is adequately provisioned and the primary bottleneck is data retrieval speed. Option D. Immediately increase the number of Spanner nodes by 50% to proactively handle anticipated load increases and buffer against potential performance issues, deferring detailed query analysis until after the peak season. Correct answer is A. Conduct a comprehensive performance analysis, including query execution plan reviews, spanner metrics examination, and workload characterization, to identify specific bottlenecks. Based on these findings, optimize inefficient queries, ensure appropriate indexing, and reevaluate the current node count and configuration for optimal resource allocation. Explanation. Scenario analysis. This scenario presents a common challenge in cloud database engineering, balancing performance optimization with cost efficiency and adherence to service-level agreements (SLAs). The challenge lies in identifying the root cause of performance degradation in Cloud Spanner, which can stem from various factors including inefficient query patterns, suboptimal schema design, or inadequate resource provisioning. Without a systematic approach, engineers might implement superficial fixes that don't address the underlying issues, leading to continued performance problems and potential SLA breaches. The pressure to deliver a performant and cost-effective solution requires a deep understanding of Cloud Spanner's architecture and best practices. Correct approach analysis. The correct approach involves a multifaceted strategy that begins with detailed performance monitoring and analysis. This includes examining query execution plans to identify bottlenecks, analyzing Spanner's internal metrics for CPU, memory, and I/O utilization, and understanding the impact of data distribution and indexing. Optimizing queries by rewriting them to be more efficient, leveraging appropriate indexes, and avoiding full table scans is crucial. Simultaneously, assessing resource allocation, such as the number of nodes and their configuration, ensures that the database has sufficient capacity to handle the workload without over-provisioning. This holistic approach, grounded in data-driven insights and best practices for Cloud Spanner, directly addresses performance issues at their source, leading to sustained improvements and compliance with performance SLAs. This aligns with the professional responsibility to ensure the reliability and efficiency of the database systems under their management, a core tenet of professional conduct in cloud engineering. Incorrect approaches analysis. A common incorrect approach is to solely focus on increasing the number of nodes without a thorough analysis of the workload. This is a brute force method that can mask underlying query inefficiencies and lead to unnecessary cost increases. Ethically, this could be considered negligent if it results in significant overspending without a clear performance benefit, potentially violating cost management principles. Another incorrect approach is to only optimize queries without considering resource allocation. While query optimization is vital, an undersized spanner instance will still struggle to execute even well-optimized queries under heavy load. This can lead to continued performance degradation and missed SLAs, representing a failure to provide a robust and scalable solution. Furthermore, making changes without proper testing and rollback plans introduces significant risk, potentially causing more harm than good and violating principles of responsible system administration. Professional reasoning. Professionals should adopt a systematic, data-driven approach to performance tuning. This involves 1. Establishing clear performance baselines and SLAs. 2. Implementing comprehensive monitoring and alerting for key spanner metrics. 3. Utilizing Spanner's diagnostic tools, e.g., query execution plans, performance insights to identify bottlenecks. 4. Prioritizing optimizations based on their potential impact and feasibility. 5. Testing changes in a non-production environment before deploying to production. 6. Continuously iterating and refining the performance tuning strategy based on ongoing monitoring. This structured process ensures that optimizations are targeted, effective, and aligned with business objectives and professional responsibilities. Question 19. Strategic planning requires a comprehensive approach to database disaster recovery in the U.S. financial services sector. Considering the critical need for data integrity and service availability, which of the following strategies best ensures a robust and compliant disaster recovery posture for a Google Cloud-hosted database? Option A. Relying on manual, infrequent testing of disaster recovery procedures only when significant infrastructure changes occur, with a focus on data replication to a cold storage solution. Option B. Replicating data to a secondary Google Cloud region but deferring comprehensive failover and failback testing until a simulated disaster event occurs. Option C. Prioritizing cost reduction by implementing a disaster recovery solution with significantly extended recovery time objectives, RTO, and recovery point objectives, RPO, without a detailed business impact analysis. Option D. Implementing automated, regular testing of failover and failback procedures to a secondary Google Cloud region, coupled with continuous data replication and documented recovery runbooks. The correct answer is D. Implementing automated, regular testing of failover and failback procedures to a secondary Google Cloud region, coupled with continuous data replication and documented recovery runbooks. Explanation: this scenario is professionally challenging because it requires balancing the immediate need for robust disaster recovery, DR, with the ongoing operational demands and cost constraints of a cloud-based database environment. The professional cloud database engineer must ensure that DR plans are not only technically sound, but also align with business continuity objectives and regulatory compliance, which are paramount in the U.S. financial services sector. Careful judgment is required to select DR strategies that offer appropriate levels of resilience without incurring prohibitive costs or excessive complexity. The correct approach represents best professional practice because it prioritizes a multifaceted DR strategy that includes regular, automated testing of failover and failback procedures. This aligns with U.S. regulatory expectations for financial institutions, such as those outlined by the SEC and FINRA, which mandate robust business continuity and disaster recovery plans. These regulations emphasize the need for documented procedures, regular testing, and the ability to recover critical systems within defined recovery time objectives, RTO, and recovery point objectives, RPO. Automated testing ensures that the DR plan remains effective and that any deviations or failures are identified promptly, minimizing potential data loss and downtime during an actual disaster. This proactive approach demonstrates due diligence and adherence to industry best practices for data integrity and service availability. An incorrect approach that relies solely on manual, infrequent testing of DR procedures is professionally unacceptable. This failure to regularly validate the DR plan can lead to undetected issues, rendering the plan ineffective when it is most needed. This directly contravenes U.S. regulatory requirements for financial institutions, which expect documented evidence of tested and validated DR capabilities. Such a lapse could result in significant financial losses, reputational damage, and severe regulatory penalties for noncompliance. Another incorrect approach that focuses exclusively on replicating data to a secondary region without comprehensive failover and failback testing is also professionally unsound. Data replication is a crucial component of DR. It does not guarantee the ability to seamlessly transition operations to the secondary site and then back again. This oversight ignores the critical need to test the entire recovery process, including application dependencies, network configurations, and user access. Regulatory bodies would view this as an incomplete DR strategy, as it fails to demonstrate a tested ability to resume full operations within acceptable timeframes. A third incorrect approach that prioritizes cost savings by implementing a DR solution with extended RTOs and RPOs without a clear business justification or risk assessment is professionally negligent. In the U.S. financial services industry, the potential impact of extended downtime or data loss can be catastrophic. Regulatory frameworks often imply or explicitly state the need for RTOs and RPOs that align with the criticality of the data and services. Implementing a DR strategy that does not meet these implicit or explicit requirements, solely for cost reasons, exposes the organization to unacceptable risks and potential regulatory scrutiny. The professional decision-making process for similar situations should involve a thorough risk assessment, understanding of business continuity requirements, and a deep knowledge of relevant U.S. regulations. This includes defining clear RTOs and RPOs in collaboration with business stakeholders, evaluating various DR technologies and strategies available on Google Cloud, and selecting a solution that provides the necessary resilience within budgetary constraints. Crucially, the process must incorporate a robust testing and validation framework, including automated testing where feasible, to ensure the DR plan's effectiveness and compliance. Regular reviews and updates to the DR plan based on testing results and evolving business needs are also essential components of professional practice. Question 20. Risk assessment procedures indicate that implementing automated CI/CD pipelines for database schema changes is a priority, but concerns have been raised about maintaining regulatory compliance, particularly regarding data integrity and security. Which of the following approaches best balances the benefits of CI/CD with these critical compliance requirements? Option A. Disable automated security checks and compliance validations for database schema changes to accelerate deployment velocity, relying on post-deployment manual audits. Option B. Focus solely on application code CI/CD, assuming that database integrity and security will be maintained through existing, separate operational procedures without direct pipeline integration. Option C. Implement CI/CD for application code, but continue to manage all database schema changes through a completely manual out-of-band process. Option D. Integrate automated security scanning, policy validation, and staged deployments with rollback capabilities into the CI/CD pipeline, coupled with an auditable approval workflow for significant schema modifications. The correct answer is D. Integrate automated security scanning, policy validation, and staged deployments with rollback capabilities into the CI/CD pipeline, coupled with an auditable approval workflow for significant schema modifications. Explanation. Scenario analysis. This scenario presents a common challenge in cloud database engineering, balancing the agility of CI/CD with the stringent regulatory requirements for data integrity and security. The professional challenge lies in ensuring that automated database schema changes, while efficient, do not inadvertently introduce vulnerabilities or violate compliance mandates. This requires a deep understanding of both CI/CD best practices and the specific regulatory landscape governing data handling within the chosen jurisdiction. The need for careful judgment stems from the potential for significant financial and reputational damage if compliance is breached. Correct approach analysis. The correct approach involves integrating automated, policy-driven validation checks directly into the CI/CD pipeline. This includes static code analysis for schema changes to identify potential security flaws or deviations from predefined standards, and automated testing against a representative staging environment that mirrors production security configurations and data masking policies. Furthermore, implementing a robust approval workflow for critical changes, even within an automated pipeline, ensures human oversight at key junctures. This approach aligns with regulatory frameworks that mandate data protection, change control, and auditability. Instance, in a U.S. context, this would align with principles found in regulations like SOX, Sarbanes-Oxley Act, for financial data integrity, and HIPAA, Health Insurance Portability and Accountability Act, for healthcare data security, both of which emphasize controlled and auditable changes to systems handling sensitive information. The automated checks and staged deployments provide evidence of due diligence and adherence to security policies, which are critical for compliance audits. Incorrect approaches analysis. One incorrect approach is to bypass automated security and compliance checks for database schema changes in favor of faster deployment. This directly violates regulatory requirements for data integrity and security, as it introduces unvetted changes into production. Ethically, it demonstrates a disregard for protecting sensitive data and maintaining system reliability. From a regulatory standpoint, this could lead to severe penalties under data protection laws, as it bypasses established controls designed to prevent unauthorized access or data corruption. Another incorrect approach is to rely solely on manual review of all database schema changes before deployment. While manual review can catch some issues, It is inherently slow, prone to human error, and does not scale effectively with frequent CI/CD deployments. This approach fails to meet the efficiency goals of CI/CD and can become a bottleneck, increasing the risk of outdated security practices or missed vulnerabilities due to the sheer volume of changes. It also makes it difficult to provide consistent, auditable evidence of compliance for every change, which is often a regulatory requirement. A third incorrect approach is to implement CI/CD for application code, but maintain a separate, manual process for database changes. This creates a disconnect between application and database deployments, increasing the risk of compatibility issues and deployment failures. It also means that database changes are not subject to the same level of automated scrutiny and rapid feedback as application changes, potentially leading to security gaps or compliance drift in the database layer, which is often where sensitive data resides and is most heavily regulated. Professional reasoning. Professionals should adopt a risk-based approach to CI/CD for databases. This involves identifying critical data assets, understanding relevant regulatory obligations, and designing automated pipelines that incorporate security and compliance gates at appropriate stages. The decision-making process should prioritize building trust in the automated process through rigorous testing and validation, while retaining human oversight for high-risk changes. Professionals must continuously evaluate and adapt their CI/CD strategies to evolving threats and regulatory landscapes, ensuring that efficiency gains do not come at the expense of security and compliance.